8 months of travel, a successful landing, you're standing on another planet, and within 60 seconds, the terrifying reality of where you are begins revealing itself, in ways no documentary, no render, no press conference ever prepared you for. Not one thing, many things. Things engineers quietly debate behind closed doors. Things buried inside mission data that never make it into the public conversation. Colonizing Mars has always been sold as humanity's greatest adventure. And maybe it is. But there's a reality sitting behind that dream, documented, measured, and scientifically confirmed, that changes the entire conversation about whether humans can actually survive there long enough to call it home. Once you see it clearly, you won't look at this dream the same way again. Now get yourself comfortable, hit subscribe. We begin. Of all the worlds in our solar system, only one looks like it could be a second home. It has a sunrise. It has seasons. It has a day almost exactly as long as ours. Mountains, valleys, and a sky that turns soft colors at dusk. Everything about it whispers that we could live there. And almost everything about that whisper is a lie. The very things that make Mars feel familiar are the same things that would end a human life on its surface faster than you could walk across a room. That single contradiction is where this story begins. Let's start with the dream itself, because it is genuinely beautiful, and it deserves to be taken seriously. The idea is simple, and it is one of the most ambitious goals any human being has ever spoken aloud. Become a 2-planet species. Stop keeping every living person, every library, every child, and every memory of our entire history on a single fragile world. Spread the risk. Build a second home, so that if something catastrophic ever happens here, an asteroid, a plague, a war we don't walk away from, the story of humanity does not simply end in the dark. SpaceX has put real numbers to that vision. The stated goal is a self-sustaining city on Mars of around 1 million people, with a target somewhere near the year 2050. 1 million is roughly the population of a city like San Jose or Birmingham, an entire metropolis lifted off this planet and set down on another one. And 2050 is not some distant abstraction. A child born today would barely be in their 20s. Many of us watching right now simply expect to be alive to see it. And so we get the image, the glass domes, the glowing city, the lone figure standing on red soil, looking out at the horizon like a settler on a new frontier. It's a powerful picture, but here is the quiet problem sitting at the center of this entire story. That picture is a rendering. It is an artist's painting of a place almost none of us have looked at closely. And the real surface, the actual rock, the actual air, the actual cold, is not a painting. The gap between the two is exactly where people could die. So let's leave the rendering behind and walk out onto the real thing. Mars is the 4th planet from the Sun, orbiting at an average distance of about 228 million kilometers, roughly 142 million miles. That is so far that sunlight, the fastest thing that exists, takes about 13 minutes to cross the gap. When you look at the Sun from the surface of Mars, you are seeing light that left it 13 minutes ago. In many ways, it is the most Earth-like world we can reach. It's about half Earth's diameter, close to 6,779 kilometers across, a little over 4,200 miles. That sounds small, until you remember Mars has no oceans. So even at half our width, the dry land of Mars is almost exactly equal to all the dry land on Earth. Every continent, every desert, every mountain range you have ever traced on a map, Mars has that much solid ground just waiting. It even keeps time the way we do. A day on Mars, scientists call it a sol, lasts about 24 hours and 39 minutes. Just 39 minutes longer than ours. Its year stretches out to 687 Earth days, almost exactly 2 of our years. So a person living there would have a birthday only about half as often. And it has 2 small moons, Phobos and Deimos. Here is a detail the people who named them clearly understood. Both moons are named for the sons of the ancient god of war. One name means fear, the other means dread, but the most important number is the one that separates us. Earth and Mars are both moving on different tracks at different speeds. When they swing close, the gap shrinks to around 55 million kilometers, about 34 million miles. When they drift to opposite sides of the Sun, it stretches to nearly 400 million kilometers, close to 250 million miles. There is no pulling over out there. There is no turning back early. Once you have committed to the crossing, the distance home is whatever the solar system decides it will be. Everything I have just told you makes Mars sound like a difficult cousin of Earth, a colder, smaller, farther sibling. That impression is the trap, because the moment you stop looking at maps and start looking at the air, the resemblance falls apart. Mars has an atmosphere. Technically, it is there, but the word thin does not begin to describe it. The pressure at the surface of Mars is about 0.6% of the pressure you are sitting in right now. Take the entire weight of the air pressing down on you at sea level and strip away more than 99% of it. To feel what that means, you would have to climb. On Earth, to reach air that thin, you would have to rise to about 30 kilometers, over 100,000 feet. That is roughly 3 times higher than a passenger jet cruise is. Mountain climbers already need bottled oxygen at 9 kilometers. Mars's entire surface, the lowest valley, the deepest basin, sits in air far thinner than the death zone of any mountain on Earth. Not slightly thinner, by an enormous margin. And at that pressure, something happens to the human body that most people have never been told. There is a threshold scientists call the Armstrong limit. It has nothing to do with the astronaut. It's named for a flight surgeon. And it marks the point where the air pressure drops so low that water begins to boil at the temperature of your own body. Not because anything is hot, because there is almost no pressure left to hold it down. Think about that for a moment. 98.6 degrees Fahrenheit, body temperature, is normally nowhere near the boiling point of water. But boiling was never really about heat. It is about pressure. Lower the pressure far enough, and a liquid simply cannot stay a liquid. It tears itself apart into vapor. On Earth, that limit sits at about 19 kilometers up, around 62,000 feet. Above it, an unprotected human is in serious trouble. And here is the part that should stop you cold. The entire surface of Mars sits well below that pressure, not near the line, roughly 10 times past it, which means everywhere on Mars, every sunrise, every plane, every spot where you might want to plant that glowing city, the air is already thin enough to boil the water inside a living body. So let's be honest about what would actually happen. Not in a movie, in reality. Step outside on Mars without a pressure suit, and the moisture on every exposed surface of your body has nowhere to go but into vapor. The saliva on your tongue, the thin film of water across your eyes, the lining of your lungs, they begin to boil, not violently, not like a kettle on a stove, more like a fizzing, the water turning to gas because nothing is holding it together anymore. And we are not guessing about this. In December of 1966, a NASA technician named Jim LeBlanc was testing a spacesuit inside a vacuum chamber when a hose came loose. The pressure around him collapsed in about 10 seconds. The last thing he remembered, just before he blacked out, was the saliva on his own tongue beginning to boil. He survived only because the team repressurized the chamber within seconds and pulled him back from the edge. That is the window. Your blood, sealed inside your veins, stays liquid. The old image of blood exploding is just a myth, but your body still loses the oxygen it needs almost instantly. Consciousness goes in about 15 seconds. After that, without rescue, death follows in roughly 2 minutes. 15 seconds to act, then nothing. 2 minutes, that's the doorstep. And suppose you solve the pressure. Suppose you sealed that air in and squeezed it up to a survivable level. You still could not breathe it. The Martian atmosphere is about 95% carbon dioxide. the same gas your own body produces as waste and works constantly to push out of your lungs. Add to that roughly 2.8% nitrogen, about 2% argon, and oxygen so scarce it barely registers, around 0.1%. For comparison, the air you are breathing at this very moment is about 21% oxygen. Mars has, for all practical purposes, none. So even pressurized, even held in, that air is not a thinner version of ours. It is a different substance entirely, unbreathable, and in those concentrations quietly lethal. There is no version of standing on Mars and simply taking a breath. The breath has to be manufactured, every single one of them. Then there is the cold. The average temperature across the whole of Mars is about minus 63 degrees Celsius, roughly minus 81 Fahrenheit. That is far below a winter day in almost any place humans have ever chosen to live. It sits closer to the heart of an Antarctic winter than to anywhere you could call home. And remember, that is the average. There are warmer moments. On a summer afternoon near the equator, the ground can climb to around 20 degrees Celsius, about 68 Fahrenheit. Genuinely pleasant. T-shirt weather, if the rest of the planet weren't trying to kill you. But hold still and wait for night to come. That same patch of ground, once the sun goes down, can plunge to around minus 70 Celsius, roughly minus 94 Fahrenheit. That is a swing of about 90 degrees Celsius, more than 160 degrees Fahrenheit, between one afternoon and that same night, in a single day. And the reason is the thin air we have been circling this whole time. On Earth, our thick atmosphere works like a blanket pulled over the planet. It holds the day's warmth long after sunset, smoothing out the difference between noon and midnight. Mars has almost no blanket at all. The instant the sun drops below the horizon, the heat radiates straight back out into space, and the surface freezes. Everything a colony builds, every pipe, every seal, every machine, would have to be heated continuously, or it would freeze and crack in the dark. Stop heating, and the planet takes it all back. Here is where the whole picture quietly turns over. We keep comparing Mars to the hardest places on Earth: Antarctica, the summit of Everest, the deep ocean floor. And that comparison feels comforting because human beings have survived all of them. But it is the wrong comparison, and the reason why is the most unsettling idea in this entire story. Every brutal place on Earth still gives you one thing for free. Antarctica is lethally cold, but you can breathe there. The top of Everest is starving for oxygen, but step outside and your eyes do not boil. On Earth, no matter how hostile the location, the air itself is never the enemy. There is always a baseline beneath you, a floor, a world that, underneath all of it, still wants you alive. Mars removes the floor. There is no place on its entire surface where an unprotected human can simply exist. Not for an hour, not for 2 minutes. The cold, the pressure, the poison, these are not whether you wait out. They are the permanent, baseline state of the whole planet, which means survival on Mars is not a question of endurance. It is a question of engineering, without pause, without exception, forever. The moment the machines stop, the planet kills you, not eventually, in minutes. That is the difference between a place that is merely hard and a place that is hostile, and Mars is the second kind. So we are left with a question the dream never quite answers. Why is Mars like this? Why would a world so similar to ours in size, in spin, in the very length of its day, turn out to be so completely, so actively deadly? And here is the part almost no one tells you. Mars was not always like this. Billions of years ago, Mars had a thicker atmosphere. It had liquid water, rivers that carved valleys still visible from orbit today, lakes that left their chemistry locked in the rock. For a long stretch of its early history, Mars may have been a genuinely livable world. Warmer, wetter, a planet with a real sky, and then it lost all of it. Here is how we know the loss is still happening. NASA's MAVEN orbiter arrived at Mars in 2014 with essentially one job: to watch the planet's air. And what the spacecraft found is that the solar wind, the constant stream of charged particles pouring off the sun, is still tearing the Martian atmosphere away and flinging it out into space right now as we speak, at a rate of roughly 100 grams every second, about a quarter pound of air. Every single tick of the clock peeled off the top of the planet and lost forever. Let that settle for a second. We are not looking at a world that was simply born dead. We are looking at a world that died. Mars is the corpse of a planet that once looked a great deal more like home, slowly stripped over hundreds of millions of years until almost nothing was left. And the same sun that warms your face this morning is still, quietly, finishing the job, which brings us back to the breath, the one you took a moment ago without even noticing, the one Mars cannot give you. We have spent this whole time on a single fact, that the air of Mars is too thin to hold pressure and too thin to hold heat. But that same thinness does something else, something we have not touched yet. Something worse. On Earth, the blanket of air over your head is not only keeping you warm, it is also stopping things, invisible things, streams of radiation, pouring out of the sun and out of the deep galaxy, falling toward every planet all the time. Our thick atmosphere absorbs them long before they ever reach the ground. It is a shield you have never once had to think about in your life. Mars has almost no atmosphere left to do that. So picture that glowing city one more time, the domes, the people walking out under the alien sky. And now ask the question the rendering will never show you. With almost no air and, as we are about to discover, no magnetic shield either, what exactly is falling on that surface every second of every day? The cold can be fought with heat. The pressure can be fought with walls. But the thing coming down through that thin sky cannot be felt, cannot be seen, and cannot ever be fully stopped. And it is already there, settling onto the ground, long before the first human being ever arrives. So, let's name the thing falling through that thin Martian sky. It is radiation, and not the gentle kind. Streams of particles moving at a staggering fraction of the speed of light, raining down from the sun and from the deep galaxy beyond it, every second, without pause. Here is the part that should unsettle you. That same rain is falling toward Earth right now, onto the roof above your head. It has been falling your entire life, and you have never once felt it. Something has been standing between you and it, silently, invisibly, for every single day you have been alive. On Mars, that something is gone. To understand what that absence means, we first have to understand what we have, and have always taken for granted. Earth defends itself with two layers, and you have lived beneath both your whole life without ever knowing they were there. The first is invisible and enormous. Deep inside our planet, an ocean of molten iron churns, hotter than the tip of a welding torch, constantly moving, constantly turning. That churning generates a magnetic field that wraps the entire planet and reaches tens of thousands of kilometers, many thousands of miles, out into space. Scientists call it the magnetosphere, and its job is to meet the solar wind, the stream of charged particles the sun is always throwing at us, and turn it aside. Picture a stone sitting in a fast river, the water splitting and curving around it. That is Earth, parting a wind of radiation that never stops blowing. Whatever slips past that magnetic field then runs into the second shield, the atmosphere, the same blanket of air that holds your warmth, the same air you have been breathing without a single thought since the moment you were born. is also thick enough to absorb most of the radiation that gets through. By the time anything reaches the ground, it has been softened into something a living body can survive. Two shields, one you cannot see, one you breathe. Together, they are the only reason life on the surface of this planet was ever possible. Now take them both away. Here is the haunting part. Mars once had the first shield too. Roughly 4 billion years ago, a span so deep it predates almost every trace of life ever found on Earth. Mars had a churning molten core of its own, and a global magnetic field to match, very likely as strong at its surface as Earth's is today. For a while, the young red planet was wrapped in the same kind of protection we still enjoy, and then slowly, it lost it. The reason is brutally simple, and it comes down to size. Mars is about half Earth's width, which means it holds far less heat, and a smaller world cools faster, the way a coffee cup goes cold long before a full bathtub even notices. As the core of Mars cooled, the churning that powered its magnetic field began to slow, and at some point, billions of years ago, the engine simply stopped. The dynamo died. The global field collapsed. What remains today is only scattered patches of ancient magnetism, frozen into the oldest rocks of the crust, the faint fingerprints of a shield that no longer exists. Across most of the planet, almost nothing remains to turn the solar wind aside. And here is the chain reaction that followed. With the magnetic field gone, the solar wind struck the upper atmosphere directly and began stripping it away, particle by particle, over hundreds of millions of years. The same slow erosion the Maven orbiter still watches happening today. The shield fell first, the air followed, and with both of them gone, the radiation that Earth has been quietly deflecting and absorbing for billions of years now reaches the Martian surface almost completely unopposed. This is the world the renderings forgot to mention. Two different threats fall on that surface, and they are not the same. The first is a constant, quiet drizzle called galactic cosmic rays, the heavy, high-energy nuclei of atoms flung out by exploding stars all across the galaxy and accelerated to nearly the speed of light. They are always there, always arriving from every direction at once, and they are devastatingly hard to stop because they punch clean through ordinary matter. Nothing breaks them. They are the background hum of the universe's violence. The second threat is sudden. When the sun erupts, a flare, a storm on its surface, it can hurl a burst of particles outward in what scientists call a solar particle event. On Earth, our shields swallow these almost entirely. On Mars, an unprotected astronaut caught in a strong one could absorb a dangerous dose in a matter of hours. The drizzle is always falling, but sometimes, with little warning, it becomes a downpour. So, how bad is it really? For a long time, that was a guess, until we finally sent something to count it. In August of 2012, NASA's Curiosity rover touched down in Gale Crater, and tucked inside it sat an instrument called RAD, the Radiation Assessment Detector. For the first time, we weren't estimating the radiation on Mars. We were measuring it directly, day after day, and the numbers it sent home are the cold heart of this entire problem. On the surface, RAD recorded an average dose of about 0.64 millisieverts every single day. That word, millisievert, is simply the unit scientists use to measure how much radiation a body absorbs and how much harm it's likely to do. To make it real, hold it against your own life. Here on Earth, from all the natural radiation around you, the ground, the sky, the air itself, you absorb roughly 3 millisieverts in an entire year. On the surface of Mars, you would absorb that much in under 5 days. Stretch it across a year, and the gap turns staggering. A single year standing on the Martian surface delivers about as much radiation as 75 years of ordinary life on Earth. An entire human lifetime of dose, packed into 12 months. And the surface is the safe part. Because during the journey there, the long months in transit, with only the thin walls of a spacecraft for cover, RAD measured nearly triple that rate, around 1.8 millisieverts a day. Every single day in deep space, your body takes on what would be roughly 7 months of natural radiation back home. Now, add it all up. A realistic mission, about 180 days out, 500 days on the surface, 180 days back, comes to a total of around 1 sievert of radiation. 1 sievert. The European Space Agency sets the entire career limit for its astronauts, everything they are permitted to absorb across a whole working lifetime, at exactly that, 1 sievert, a whole career's worth of radiation, spent on a single trip. And it carries a price. That 1 sievert career limit is tied to roughly a 5% rise in the lifetime risk of dying from cancer. NASA draws its line even tighter. Its standard works to keep an astronaut's added risk of fatal cancer at no more than 3%. A round trip to Mars would sail straight past that line and keep on going, which sets up a genuine disagreement among very serious people. When the Curiosity team published those first numbers, the word they reached for was manageable, survivable, they argued, for a finite exploration mission flown by informed volunteers who knowingly accept the risk. But measured against NASA's own 3% cancer limit, that identical dose reads not as manageable, but as a showstopper, a number that breaks the rules the agency wrote to keep its own people alive. Both sides are staring at the exact same figure. They simply disagree about how much a human life is allowed to absorb, and the cancer risk, as serious as it is only the first item on the list. Let's be honest about something first, because it matters. No astronaut has yet been confirmed to have died from a cancer caused by space radiation. The doses humans have taken so far have been far smaller, and cancer can take decades to surface. So much of what we know comes from other places: survivors of the atomic bombings, patients treated with radiation therapy, and animal studies. But every one of those sources points in the same troubling direction, and the heavy particles in deep space may do a kind of damage that is worse, not gentler, than anything we have studied on the ground. The eyes are vulnerable. Chronic radiation slowly clouds the lens, seeding cataracts. The heart is vulnerable. Studies link this exposure to a higher risk of cardiovascular disease, the gradual fraying of the vessels that keep you alive. The brain may be vulnerable too. Animal data tie this kind of radiation to measurable effects on memory and cognition, raising the deeply unsettling possibility that the very organ doing the thinking could be worn down by the trip itself. And then there is the deepest cost of all. The cells that make the next generation, sperm and egg, are among the most radiation sensitive in the whole entire body. Heavy exposure raises the risk of sterility, and damage to those cells can be inherited, raising the risk of birth defects in any children. The radiation does not only threaten the traveler, it reaches forward toward everyone who might come after them. So the answer seems obvious. If the danger falls from above, you go below, you hide, and you can. That is the cruel elegance of this problem. The solution exists. It is almost within reach, and it still does not set you free. To block galactic cosmic rays, you bury the habitat. You pile Martian soil, the loose rock and dust called regolith, over the roof. But these particles are so penetrating that a thin layer does almost nothing. You need it thick. 1 meter of regolith, a little over 3 feet, cuts the radiation by only about 40%. For real protection, for a true storm shelter, you are talking several meters of soil overhead, perhaps 10 feet or more, hundreds of tons of dirt, pressing down on a structure that must somehow hold all that weight, while simultaneously holding pressurized air inside, straining outward against the vacuum. The walls would be fighting in 2 directions at once, but suppose you manage it. Suppose you build the buried bunker. Here is the trap closing. The instant you pile material overhead to stop the cosmic rays, those rays slam into the soil and shatter its atoms. And out of that collision comes a brand new kind of radiation. Secondary neutrons sprayed downward into the very space you were trying to protect. And neutrons are not a lesser danger. Drop for drop, they can be far more biologically damaging than the particles that created them. Add too little shielding, and the cosmic rays come straight through. Add shielding, and you manufacture a second threat inside your own shelter. The protection bites back, and one more wall completes this trap, the one that may matter most. Anything that has to stay transparent cannot be buried at all. Your windows, your view of the sky, and above everything else, your greenhouses, the crops that must see sunlight to grow, the food the whole colony lives on. You cannot bury a greenhouse under 3 meters of rock, which means the plants you depend on for survival must sit out in the open, soaking in the very radiation you are hiding from. Here is the contradiction Earth never forces on you. Our atmosphere does 2 jobs at the same time. It shields us, and it lets the light through. It protects you without ever once asking you to choose. On Mars, those 2 things split apart and become enemies. To be safe, you must live in the dark, underground, blind to the sky. To eat, to grow, to see, you must step back out into the fire. Safety and life pulling in opposite directions, and no amount of engineering can ever fully reconcile them. So where does that leave the dream of a city on Mars? Not at impossible, but somewhere far stranger and far more sobering than a glowing dome on an open red plain. The honest version of a Martian settlement is mostly underground. People living beneath meters of soil or tucked deep inside lava tubes. Vast natural tunnels left behind by ancient volcanoes. Some of them possibly large enough to shelter entire communities under a roof of solid rock. Tanks of water and blocks of ice stacked around the sleeping quarters, not only to drink, but because the hydrogen in water is one of the finest materials in existence for soaking up those deadly neutrons. A life lived in large part in the dark, and it can be done. The dose can be lowered. That is the real, hard-won reassurance buried in all of this. Survival on Mars is not a fantasy. It is an engineering problem with partial solutions, and clever people have already sketched most of them out. But lowering the dose is not the same as erasing it. There is no wall thick enough, no tunnel deep enough to make the surface of Mars truly safe. Not the way the ground beneath your feet at this very moment is safe, without your ever once having to think about it. The radiation can be reduced. It cannot be defeated. And the ones who would absorb the most of all are exactly the ones with the least protection. The crew crossing open space to get there, and any child unlucky enough to be conceived on a world with no shield. But all of this, the buried bunkers, the shielded shelters, the meters of soil heaped overhead, rests on one quiet assumption we have not yet questioned, that the soil itself is something you would actually want to surround yourself with, that the ground you would bury your home inside is at worst just dirt. It isn't, because the same Martian regolith that engineers want to pile over our heads to save us from the sky is hiding something inside it that no one bargained for, a chemistry that exists in no garden, no field, no handful of soil anywhere on Earth, something that poisons the water, corrodes the machines, and turns the simple act of growing food into a struggle against the very ground you are standing on. We came down to Mars afraid of what was falling from above. We are about to discover that the danger was also waiting in the dust, in the very ground we would have to dig into, breathe around and live inside every single day. So let's pick up a handful of that ground, reach down in your imagination and scoop up a fistful of Martian soil. It looks almost familiar, rust-red, dry, fine-grained, like dirt from a desert canyon or a sun-baked riverbed somewhere on Earth. You could almost mistake it for home, and that is exactly the problem. because this is the single most abundant resource on the entire planet, the thing a colony would build its walls from, bury its habitats beneath, and try somehow to grow its food in. We would be touching it, breathing near it, and living inside it every single day. And hiding in that ordinary-looking dust is a poison that exists in no garden anywhere on Earth. The story of how we learned this begins in 2008, with a small NASA lander called Phoenix, sitting in the frozen plains near the Martian North Pole. Phoenix scooped up a sample of soil, mixed it with water it had carried from Earth, and ran a simple chemistry test. And what it measured caught the entire science team off guard. Finding calcium perchlorate was one of our most unexpected results, said Peter Smith, the mission's lead scientist at the University of Arizona. He admitted that the word was so unfamiliar, the whole team had to go and look it up. So let's be clear about what perchlorate actually is. It's a type of salt, a chemical compound built around chlorine and oxygen. And on Earth, it's mostly something we manufacture for rocket fuel and fireworks and road flares. It barely occurs in nature here, but on Mars, it's simply lying in the soil, everywhere. Phoenix measured it at roughly 0.5% of the soil by weight, between about 0.4 and 0.6%. That sounds tiny, almost negligible, but hold that number for a moment, because 0.5% of an entire planet's surface is not a trace, it is a feature, and it was not a fluke of one location. Later measurements, from orbit and from the Curiosity rover halfway across the planet, point to the same conclusion. The perchlorate is almost certainly everywhere, distributed across the whole of Mars. The poison isn't in one unlucky spot you could simply avoid. It's in the ground beneath every place you might ever want to land. Here is why that matters for a human being. Perchlorate has a specific, well-understood effect on the body. It interferes with the thyroid, the small gland in your neck that runs your metabolism. It does this by blocking the thyroid's ability to take up iodine, the raw material it needs to make its hormones. Starve the thyroid of iodine, and its hormone production falters. We actually know this effect intimately, because doctors on Earth once used perchlorate as a medicine, in careful doses, to treat people whose thyroids were dangerously overactive. But a Martian colonist would not be taking a careful medical dose. They would be living in a world where the dust is laced with it. The safe daily exposure limit is vanishingly small, and just a few milligrams of Martian dust tracked in on a boot or breathed off a dirty surface would already cross that line. Chronic exposure raises the risk of an underactive thyroid, and there's evidence it can damage the lungs as well. And the chemistry is aggressive in another way too. Perchlorates are powerful oxidizers, chemically hungry, prone to corroding metal and attacking the organic molecules that living things are made of. This is dust that doesn't just sit there, it works on whatever it touches. Now, before this becomes purely grim, here is the twist that keeps Mars interesting. That same poisonous salt is also a hidden resource. Because perchlorate is so rich in oxygen, it can, in principle, be broken down and processed to release that oxygen, for breathing or for fuel. The thing trying to wreck your thyroid is also potentially a source of the air you need. On Mars, almost nothing is simply good or simply bad. Everything is both. Which brings us to food. The dream of a self-sustaining colony rests entirely on growing crops. And the obvious idea is to grow them in Martian soil. But you cannot plant a seed in perchlorate-laced dirt and expect it to live, because the salt is toxic to plants just as it is to people. Before that soil could ever support a garden, it would have to be washed, flushed repeatedly with water to rinse the perchlorate out. And there is the trap, quietly closing. To clean the soil, you spend water, the scarcest, most precious substance on the entire planet. And the water you use doesn't vanish. It comes out the other side as contaminated wastewater, now full of toxic salt, which then has to be treated and managed all over again. The simple act of preparing a field to grow food becomes a chemical processing operation that drains your most limited resource. The ground does not want to feed you. It has to be forced, and the dust itself fights you in a way that has nothing to do with chemistry. Martian dust is extraordinarily fine, 5 to 10 times finer than the baby powder in a bathroom cabinet, with individual grains averaging just a few millionths of a meter across, far too small to feel as anything but the softest silt, and it carries a static electric charge, which means it clings to everything, the way a styrofoam packing peanut sticks to your hand and won't shake off. That is how this dust behaves with suits, seals, hinges, camera lenses, and the fine joints of every machine. We learned exactly how stubborn this kind of dust can be, and we learned it on the moon. The Apollo astronauts were tormented by lunar dust. It abraded their visors, worked its way into the seals of their suits, and when they tried to brush it off their equipment with a simple whisk broom, they largely failed. At one point, the dust-caked radiators on their rover came close to overheating, and those were missions that lasted days. A Mars colony would mean years of exposure to a dust that is not only just as clinging, but toxic on top of it. Every airlock cycle, every walk outside, would track a little more of it inside, into the lungs and the machinery, where it does not belong. But you can survive toxic soil if you stay sealed away from it. What you cannot survive for even a few days is the absence of water. A human being needs somewhere around 2 to 3 liters of water a day simply to drink, and once you add cooking, cleaning, and basic hygiene, daily use climbs into the tens of liters per person. Water is not a luxury on Mars. It is the thread every single life hangs from. And here is the brutal fact about that thread. Mars has no water cycle. None. No rain falls, no rivers run, no clouds gather to replenish anything. Whatever water a colony uses is not refilled by the planet, ever. On Earth, you turn a tap without a thought, because an entire planetary system, oceans, evaporation, weather, is constantly recharging the supply. On Mars, there is no recharge. There is only what you can find and what you can keep. Water does exist there. That part is real. Thick caps of ice sit at the poles, and vast amounts of ice lie frozen into the soil beneath the surface. But getting usable water from buried ice is an industrial ordeal. You have to excavate it, heat it to melt it, condense the vapor, and then purify it. And every one of those steps devours energy you may not be able to spare. And then, in 2024, came a discovery that sounded at first like salvation. A team of scientists led by researchers at the University of California, working with seismic data from NASA's InSight lander, announced evidence for something staggering: a huge reservoir of liquid water locked deep inside the Martian crust. Not ice, liquid. Possibly enough if you could somehow spread it across the surface to cover the entire planet in an ocean 1 to 2 kilometers deep, well over half a mile. For a moment, that sounds like the answer to everything, and then you read where it is. That water sits between roughly 11.5 and 20 kilometers down, about 7 to 12 miles beneath the surface. To grasp what that means, consider this. The deepest hole human beings have ever drilled anywhere, the Kola borehole in Russia, reached just over 12 kilometers, and it took around 20 years of effort, with the full weight of industrial civilization behind it, on Earth. The shallowest edge of that Martian water lies as deep as the deepest hole we have ever managed to dig. For an early colonist with a few machines on a frozen, distant world, it might as well be at the center of the planet. The ocean is real, and it is completely out of reach. And here the story splits into a genuine scientific fight that is still unresolved. The 2024 team argued the seismic data are best explained by liquid water filling cracks in the rock. But in 2025, other scientists, including a study led by the Mars researcher Bruce Jakosky, pushed back, arguing that the very same data do not require liquid water at all. The signal could just as easily come from solid ice, or from minerals cementing the rock, or from pores that are simply empty. Both sides are reading the identical measurements from the same dead lander. One sees a hidden ocean, the other sees rock that might be bone dry. We do not yet know who is right, and until a future mission can probe deeper, the question of how much water Mars is truly hiding remains genuinely open. What is not in dispute is the part that matters for a colony. Whatever is down there, it is unreachable, which leaves the settlers depending on recycling, reusing every drop they bring or dig over and over. The International Space Station already does this, and does it impressively well, recovering somewhere around 93% of its water for years, recently pushed as high as 98%. But think about what the missing few percent means when you can never refill. That loss isn't a one-time cost. It happens every cycle, every day, forever, and across a base of 100 people over a year, those small percentages compound into tons of water that simply disappear and must somehow be replaced from Martian ice. A leak you can never fully stop on a world that will never give the water back. Then there is the air itself and the question of whether we can make our own. The good news is that we have actually tried it. Riding aboard the Perseverance rover, which landed in 2021, was a microwave oven-sized device called MOXIE, built by MIT, with one job: to pull breathable oxygen out of the thin Martian carbon dioxide. And it worked. Across its mission, MOXIE made oxygen 16 separate times, a real history-making proof that it can be done. But now look at the scale, because the scale is humbling. In its entire run, across 2 years, MOXIE produced a grand total of 122 grams of oxygen, which NASA cheerfully noted is about what a small dog breathes in 10 hours. At its very best, it managed 12 grams in an hour. A single human being needs more than 800 grams of oxygen every single day. One astronaut would breathe through MOXIE's entire lifetime output in just a few hours. To keep even a small crew alive, NASA estimates you would need a version of this machine roughly 200 times larger, paired with a dedicated power plant generating 25 to 30 kilowatts. That is enough electricity to run something like 24 average homes, devoted entirely to making the air for one base. The proof of concept is genuine. The gap between that proof and a breathing colony is enormous. And every single thing I've just described, washing the soil, melting the ice, running the air machine, holding back the cold, every one of them runs on power, which is exactly where Mars plays its cruelest card. First, let's clear away a myth, because the movies have it badly wrong. You may picture a Martian dust storm as a screaming, hurricane-force gale strong enough to hurl people and topple rockets, the way the film The Martian famously opens. It isn't. The author of that story, Andy Weir, has openly admitted he exaggerated it. In reality, he said, a Martian dust storm could barely knock over a piece of paper. The reason is the thin air. Even when Martian winds reach 60 miles an hour, around 100 kilometers an hour, the atmosphere is so sparse that the force you'd feel is closer to a gentle 6-mile-an-hour breeze on Earth. The wind is not the danger is the darkness, because these storms throw so much dust into the sky that they blot out the sun, and they can swallow the entire planet and last for weeks, sometimes months. We measure how much sunlight the dust blocks with a value called optical depth, or tau. On a clear Martian day, tau sits around 1/2. During the Great Global Storm of 2018, over the Opportunity rover, it climbed to somewhere near 10.8, more than 20 times as thick. A tau of just 1 already blocks well over half the sunlight. At nearly 11, almost nothing gets through. As the Opportunity team's project manager described it, the skies went so dark it was, in his words, nighttime during the day, and for a machine that lives on sunlight, that is a death sentence. Opportunity ran on solar panels. It had rolled across Mars for more than 14 years, a rover built to survive just 90 days that lasted over 60 times its design life. Then the 2018 storm closed over it like a lid. The panels went dark, the batteries drained, and on June the 10th, 2018, it sent its final fading transmission, an incomplete image, the bottom third dissolving into black, where the signal simply stopped. It never woke up. 4 years later, the InSight lander died the same slow way, its panels gradually smothered under dust until the power fell below the line that kept it alive. Robots, killed by the dark. Now put people there instead. So step back and feel the full shape of what the surface of Mars actually is. It is not a neutral place that merely lacks what we need. It is a place that actively withholds. The soil hides a poison and demands water to clean. The water hides kilometers underground or leaks away in recycling. The air must be manufactured, machine by straining machine. And the one free gift the planet seems to offer, sunlight to power it all, can be switched off without warning for months at a stretch. And yet, and this matters, none of it is flatly impossible. The soil can be washed, the ice can be mined, the oxygen can be scaled up. The dark months can be survived with enough stored power. Smart, determined people have already worked out the outline of how. The honest truth is not that a Martian colony can't be supplied. It's that every solution feeds on the very things that are rarest: water, energy, and mass hauled across the void, and the planet fights you for each one. This is not living off the land. There has never, in all of human history, been a frontier like this. Every other place we have ever settled at least wanted, in some small way, to keep us alive. Mars does not. But notice what every single one of those solutions had in common: washing the soil, melting the ice, making the air, pumping the heat, surviving the months of darkness. Underneath all of them, holding the entire colony above the abyss, sits one thing, and one thing only: power, energy, the current that keeps the heaters warm, the recyclers running, the air machines breathing. And we have just seen the catch. Mars has no oil and no coal. It never had the ancient life to make them. It has almost no wind that can push against anything. Its rivers dried up billions of years ago, and the sunlight that might save it vanishes without warning for weeks or months at a time. Pull that power for even a few hours, and it does not fail gently. The heat dies, and the cold comes in. The recyclers stop, and the water is lost. The air machines fall silent, and the oxygen begins to run down. Everything we've built fails together, all at once in the dark. So the question that now decides whether anyone lives or dies on Mars is brutally simple. On a frozen, fuelless world where the sun itself cannot be trusted, where does the power actually come from? And what exactly happens in the hours after it fails? So let's answer that question directly, because everything now depends on it. On Mars, power is not one system sitting among many others. Power is the floor under all of them. The heat that keeps your blood from freezing, electric. The pumps that hold the air pressure inside your walls, electric. The machines that recycle your water, melt your ice, scrub your air, and grow your food. Every one of them, electric. Cut the power on Earth, and you light a candle and wait for morning. Cut the power on Mars, and the cold pours in, the air thins, the water is lost, and the food dies, all at once in the dark. So the colony's whole survival collapses into a single question: where does the energy come from? And when you go looking for the answer, you discover that nearly every source humanity has ever relied on is simply not there. Let's go through them, one by one, and watch them fall away. Start with the source that built our entire civilization: fossil fuels. Coal, oil, natural gas. We burn them without thinking, but stop and consider what they actually are. They are the compressed remains of ancient life, forests and oceans of organisms that lived, died, and were buried over hundreds of millions of years, their stored sunlight slowly pressed into fuel. Mars never had that. No forests, no teeming seas, no deep history of life to leave its body behind in the rock. The planet has been barren for billions of years, which means there is not a single lump of coal, not one drop of oil, anywhere on it. That entire option doesn't just fail, it never existed. Then there's hydroelectric power, the energy of falling water turning turbines in our dams. But we have already seen that Mars has no rivers, no flowing surface water of any kind. Nothing falls, nothing flows, so nothing turns. What about wind? Mars certainly has wind, but recall the thin air. The atmosphere is barely 1% as dense as ours, and the force a wind can deliver depends on how much air is actually moving against the blade. 1% of the air means roughly 1% of the push. A Martian gale that looks dramatic carries almost no power at all. Wind turbines, the workhorses of clean energy on Earth, would stand on Mars as little more than slowly turning sculptures. And just like that, the familiar world is stripped away. No coal, no oil, no gas, no hydro, no meaningful wind. We are left with exactly two real ways to keep a colony alive. The first is the obvious one: the sun. Solar power. And it does work on Mars, in the right place. But the sun that falls on Mars is not the sun we know. Because Mars orbits so much farther out, the sunlight reaching it carries only about 43% of the strength it has at Earth, even with a perfectly clear sky and the sun directly overhead. Less than half. The brightest Martian noon delivers roughly the light of a gloomy winter's day in northern Canada or northern Europe. That is the good scenario, and we have already seen the bad one. When a great dust storm rises and the sky goes dark for weeks or months, solar power doesn't just dip, it collapses, falling to a small fraction of an already weak supply for longer than any human can simply hold their breath and wait. To survive that, you would need banks of batteries vast enough to power an entire base in the dark for months, and batteries that large are crushingly heavy to ship and fiendishly hard to build and maintain, which leads to a hard, unavoidable conclusion. For any serious permanent colony, betting your life on sunlight alone is a gamble the planet will eventually win. Reliable power, the kind that doesn't care whether the sun is shining, becomes not a luxury, but a requirement. And there is only one source that offers it. Nuclear fission, splitting atoms to release heat, gives steady power regardless of weather, regardless of dust, regardless of whether it is day or deep polar night. It simply runs. And this is not science fiction. We have already built and tested a version designed for exactly this. NASA, working with the Department of Energy, developed a compact space reactor called Kilopower, and in 2018, in the Nevada desert, they ran its prototype, a reactor nicknamed Krusty, at full power for 28 straight hours. At the heart of it sat a core of uranium so small you could hold it in one hand, about the size of a paper towel roll. From that, the system produced kilowatts of steady electricity. As the chief designer, David Poston of Los Alamos, put it, they threw every kind of failure they could at the reactor, and it passed with flying colors. But now, weigh that achievement against what a colony would actually need. A single kilopower unit produces around 10 kilowatts, enough to run several average homes. The larger systems now being designed aim for 40 kilowatts, enough to power roughly 30 households continuously. Impressive, and nowhere near enough. A base of 100 people would likely need at least a full megawatt of power, running around the clock, the steady draw of roughly 1,000 homes. That's 25 of those larger reactors, or 100 of the tested ones, all operating at once. And a truly industrial colony, one that could actually build things, refine metals, manufacture its own parts, would need tens of megawatts, an entire fleet of reactors humming away beneath the red soil. We have proven the spark. We have not remotely built the fire. And power, as enormous as that challenge is, only keeps the lights on. It does not by itself put food in anyone's mouth. A human being needs somewhere between 2,000 and 3,000 calories every single day just to keep functioning, and the relentless physical labor and stress of survival on Mars would push that number higher. So the obvious first answer is simply to ship the food from Earth, and for the first small cruise we will. But as a permanent solution, it fails on pure arithmetic. Consider the rocket meant to carry it, SpaceX's Starship, designed to haul somewhere around 100 tons to the Martian surface. That sounds like a mountain of supplies, but fill an entire Starship with nothing but food, and it would feed 100 people for only a few years before the last of it was gone. Then you need another, and another, forever, every 26 months across tens of millions of miles, at staggering cost. A colony that eats only what Earth sends is not a colony. It is a very expensive, very fragile mouth that Earth must feed until the day it stops, which means the dream demands something far harder. The colony has to grow its own food on Mars, and that opens a whole new front in the war with the planet. Picture the greenhouse, glass walls, green rows, sunlight streaming in. Now remember where it stands. Outside is a near vacuum, so that cheerful greenhouse must be pressurized to keep its plants and its air from boiling away, holding something like 100 times the pressure of the world outside, every pane and seam straining outward, the entire structure permanently trying to burst like an overinflated balloon. One crack, and the garden dies in minutes. But suppose it holds. There is a deeper problem, and it comes down from the sky. To let sunlight reach the crops, the roof has to be transparent, and transparent glass cannot stop the radiation we spoke of earlier. In 2021, a team of Dutch researchers at Wageningen University put this to the test, led by an ecologist who calls himself a space farmer. Frustrated by film scenes of happy Martian greenhouses, they grew rye and garden cress under cobalt sources tuned to mimic the gamma radiation of the Martian surface, radiation that runs perhaps 17 times stronger than on Earth. The result, after just 28 days, was grim. The irradiated plants came up stunted and dwarfed, their leaves browning, their harvest sharply reduced. Their honest conclusion: growing crops in a surface greenhouse on Mars may simply not work very well. We should be careful here. Recreating space radiation on Earth is imperfect, and the final answer will only come from growing real plants on Mars. But the warning is clear enough, so you do the only thing left. You move the farm underground, beneath meters of protective rock, safe from the radiation at last. And in doing so, you blot out the sun entirely, which means every single calorie must now be grown under artificial light, drinking yet more of that precious, hard-won power. And these are not small gardens. Estimates suggest each person needs somewhere around 50 to 100 square meters of growing area to be fed, roughly the floor space of a small apartment each. For a colony of 100, that is acres of lit, heated, pressurized farmland buried in the dark, and the soil it grows in must first be stripped of its poison, the perchlorate washed out, and then rebuilt, almost from nothing, into something a root can live in. Step back, and you see what all of this really is. Not a base, a bubble, a single sealed world in which the air, the water, the waste and the nutrients must all cycle round and round endlessly, with almost nothing coming in and almost nothing going out. Every breath of carbon dioxide has to be turned back into oxygen, every drop of water recovered, every scrap of waste broken down and fed back into the soil. A closed loop, sustaining human life, sealed against a dead planet, and it has to work perfectly for years, without fail. We have tried to build that loop here on Earth, where help is always one phone call away, and what happened should give everyone pause. In September of 1991, 8 people sealed themselves inside a vast glass enclosure in the Arizona desert called Biosphere 2, a beautiful, ambitious attempt to build a tiny, self-contained Earth, complete with a rainforest, an ocean, and a farm. The plan was to live fully sealed, growing their own food and breathing their own recycled air for 2 years. It was meant as a rehearsal for exactly this, a colony on another world, and slowly it began to come apart. The oxygen inside started to fall. Quietly, mysteriously, month after month, the breathable air thinned until it reached the kind of level you'd find near the top of a tall mountain, where the body labors for every breath and the mind grows dull. The crew were struggling to function. In the end, managers had to pump oxygen in from outside, which meant the sealed world was no longer sealed. The food ran short too. Over the mission, the crew lost on average around 16% of their body weight, slowly starving inside their own garden. The pollinating insects they'd brought all died, forcing the people to pollinate their crops by hand, flower by flower. Of 25 small animal species, 19 went extinct, and under the strain, the 8 humans themselves fractured, splitting into 2 bitter factions who could barely speak to one another. Oxygen gone, food short, pollinators dead, the crew at war, and all of it inside a glass house on Earth with breathable air just outside the door. Now, to be fair, that is not the whole story. An earlier and smaller experiment, the Soviet project called Bios 3 in Siberia, did better in some ways, sustaining a crew of 3 for up to 180 days while recycling essentially all of their air and 95% of their water. A real, genuine achievement. But notice the catch buried inside that success. Only 3 people, only half their food grown inside, the rest shipped in. And here is the cruel pattern that ties both experiments together. The smaller and simpler you make a closed world, the more controllable it becomes. But the more people you add, the more complexity, the more ways it can quietly fail. Mars asks for the largest, most complex closed ecosystem ever attempted, for the most people, with the least margin for error and the farthest from any rescue. That is the contradiction at the heart of self-sufficiency. To truly stand alone, the loop must be perfectly, completely closed. And the more completely you close it, the more catastrophically it falls apart when a single piece breaks. And breaking pieces is the part no one can engineer away. On Earth, when something fails, a replacement is a day away. On Mars, the next ship might be 2 years out. So the colony must make its own spare parts, its own tools, its own repairs, out of whatever the planet provides. 3-dimensional printing helps. You can melt local material and print simple shapes, but you cannot print a computer chip. You cannot print a solar cell, a precision pump, a medical sensor, a microprocessor. The intricate electronics that run every life support system on Mars can only be made for now by the vast industrial web of Earth, thousands of specialized factories, mines, and supply chains that took us 2 centuries to build. Pulling raw materials from Martian rock and air to make what you need, what engineers call in situ resource utilization, is absolutely essential and almost entirely unproven at the scale a city would demand. Add it all together and an honest answer emerges. True industrial independence, a Mars colony that could actually survive if Earth went silent, is most likely 50 to 100 years away, if it is ever truly possible at all. Which means the phrase self-sustaining city hides something the renderings never show. For a very long time, perhaps generations, a Mars colony would not be self-sustaining at all. It would be something closer to a patient in intensive care, alive only because it stays wired to a machine, and that machine is Earth, and the cord connecting them is a narrow launch window that opens just once every 26 months. But notice what we have been doing this whole time. We have been talking about Mars as a machine to be built, power and food and air and water, systems to be engineered, problems to be solved. And if that were the whole story, it would be merely the hardest construction project in human history. It isn't the whole story, because there is another machine in this picture, sitting inside every spacesuit, inside every sealed habitat, one that no reactor can power and no greenhouse can feed, the human body. And that body was not designed for Mars. It was tuned over millions of years, atom by atom, to one specific world, its gravity, its rhythms, its pull. We're about to take it somewhere it has never been, hold it there for years, and ask it to keep working. We do not fully know what happens when we do. We do not know what a lifetime in a third of Earth's gravity does to human bone or to the human heart. And we do not know the most haunting thing of all, whether a child conceived on Mars could ever safely be born at all. So let's look closely at that body, the one machine on Mars that no one designed and no one can replace, because the human body keeps a hidden ledger and almost no one ever notices it. Every day of your life, in perfect silence, your bones, your muscles, your heart, and your blood are all quietly measuring one single force, the pull of the Earth beneath you, and adjusting themselves to match it. You have never felt this happening. You don't have to. It runs on its own beneath every thought, calibrated over millions of years to one exact number. And we are about to take that body to a place where the number is wrong. Not for a moment, for years. And the truth is, we have almost no idea what happens when we do. Let's be precise about what's actually different. The gravity on the surface of Mars is about 38% of Earth's, a little over a third. That sounds abstract, so make it physical. A person who weighs 150 pounds here would weigh only about 57 pounds standing on Mars. Pick up a heavy bag of groceries, and on Mars it would feel almost empty in your hand. You could leap slowly, half again, as high as you ever have. To the imagination it sounds delightful, a gentler world where everything is light. But your body does not experience gravity as a feeling. It experiences it as an instruction. The constant weight pressing down through your skeleton is the signal that tells your bones how dense to stay. The effort of holding yourself upright is what keeps your muscles thick and your heart strong. Gravity is not a burden the body merely endures. It is the resistance the body was built around, the daily workout it never gets to skip. And here is the unsettling part. The body is ruthlessly efficient. It will not maintain anything it is no longer asked to use. Take away most of the pull, and the body, sensing it is no longer needed, begins quietly to let itself go. We know this is true because we have watched it happen in the most extreme version of all. Not on Mars, but in the near total weightlessness of the International Space Station, where astronauts have floated for months at a time, and the data they've brought home is sobering. Start with the skeleton. In the weightlessness of orbit, an astronaut's weight-bearing bones, the spine, the hips, the long bones of the legs, lose roughly 1 to 2% of their density every single month. Let that number breathe for a moment, because it is worse than it sounds. A woman past menopause, considered at real medical risk for fragile bones, loses bone at about that same rate, but per year. An astronaut loses in a single month what she loses in 12. 6 months in orbit can drain a year's worth of bone at a pace nearly 10 times that of osteoporosis. The muscles go the same way, only faster. With nothing to push against, the great muscles of the legs and back the ones that fight gravity all day on Earth, begin to waste away, shedding as much as 20% of their mass in a matter of weeks. The heart, which on Earth labours every second to pump blood upward against gravity, suddenly finds its job made easy, and like any muscle with less to do, it weakens and shrinks, so thoroughly that when astronauts return, many simply cannot stand without feeling faint, their deconditioned hearts unable to keep blood in the brain against the weight of the world. In some studies, well over half of returning crews struggle to stay upright in their first hours back. And it doesn't stop there. Without gravity pulling the body's fluids down toward the feet, they drift upward instead, pooling in the head, giving astronauts puffy, swollen faces and raising the pressure inside the skull, pressing on the back of the eyes. Over time, this can physically reshape the eyeball and blur an astronaut's vision, a condition that can linger long after they've come home. Even the immune system falters. Under the stress, dormant viruses that most of us carry quietly for life, the ones behind chickenpox and shingles, can stir back awake and begin shedding inside the body. Bone thinning, muscle wasting, heart shrinking, eyes deforming, defenses failing. That is what the absence of gravity does to a human being. But now we arrive at the single most important fact in all of this. And it is a fact about what we do not know. Everything I just described comes from near-zero gravity, from floating. And Mars is not zero gravity. Mars is a third, which raises the one question everything depends on, and which no one on Earth can currently answer. What does a third of gravity do? Here is the trap hidden inside the science. We understand the human body at one full gravity. We have all of human history for that. And now we understand it at almost zero gravity. Decades of spaceflight have shown us that. But between those 2 points lies an enormous, unexplored blank. No human being has ever lived in sustained partial gravity. Not for a month, not for a year, not ever. We have the two ends of the rope and nothing whatsoever in the middle. So perhaps a third of gravity is enough. Perhaps that gentle, steady pull is sufficient to keep bone dense and muscle strong, and the damage of weightlessness simply never sets in. Many scientists genuinely hope so, but perhaps it isn't. Perhaps the body needs nearly a full Earth's pull to stay whole, and a third falls below some invisible threshold, so that a colonist's bones and heart slowly degrade anyway, just more gradually, over years instead of months. We do not know which of those is true. We have never run the experiment, and the first people to find out will be running it on their own bodies, with no way to undo the result, and that result might be a door that locks behind them. Because if a body spends years adapting to a third of gravity, letting its bones thin and its heart ease to match this lighter world, then coming back to Earth would not feel like coming home. It would feel like being crushed. Imagine standing up after years on Mars and feeling your own body suddenly weigh roughly 2.5 times what you had grown used to. Every step a strain, your weakened heart laboring, your thinned bones bearing loads they no longer remember. For some, returning to the gravity of their own birth planet could mean broken bones, or a heart that cannot cope. The longer you stay, the more Mars rewrites you, until Earth itself becomes a place your body can no longer survive. And if that is true for an adult who arrived fully grown, then it forces a far darker question about anyone who might be born there. Because a colony that wants to last cannot be filled forever by ships from Earth. To truly endure, it would need children, human beings conceived, carried, and born on Mars. And this is the deepest unknown of them all. We genuinely do not know whether a human being can be made on another world. We have taken the very first, tentative step toward an answer. In 2023, a team of Japanese scientists led by the biologist Teruhiko Wakayama, working with the space agency JAXA, did something quietly historic. They sent frozen mouse embryos up to the International Space Station, where an astronaut thawed them by hand and let them grow for 4 days in the weightlessness of orbit. And the embryos developed, dividing normally, reaching the stage called the blastocyst, the tiny cluster of cells that would go on to form the body and the placenta. Gravity, at least at this earlier spark of life, seemed to make no real difference. It was a genuine, remarkable result. But look carefully at how small that result really is. The experiment lasted only 4 days, the very beginning of the very beginning. Of the embryos that came back, only around a quarter had formed those healthy clusters. And it tested microgravity, not Martian gravity. Everything that matters most about making a new human, implanting in the womb, 9 months of gestation, the act of birth itself, and the long years of a body growing from infant to adult, all of it remains completely untested in low gravity. Not one mammal has ever been carried to term and born anywhere but Earth, and separate studies hint that the radiation of space can damage the DNA inside reproductive cells, though, encouragingly, in some experiments mouse sperm stored for years in orbit still produced perfectly healthy pups. The picture is not hopeless, but it is almost entirely blank, and here is where the question turns genuinely haunting. Suppose a child is conceived and born on Mars, and grows up there, its bones forming, its heart developing, its whole body taking shape in nothing but a third of Earth's gravity. That body might calibrate itself perfectly to Mars, and in doing so, it might become a body that could never survive on Earth at all. Too weak, too fragile, its heart never built for our heavier world. The first human born on Mars might be physically unable to ever set foot on the planet their entire species came from. A native of a world their parents chose for them, exiled by their own biology from the home of all human history, and unable, as an infant, to have agreed to any of it. That is not a problem engineering can solve. It is a question about whether it is right to create a life when we cannot yet promise that life a body that works. And while those vast unknowns hang over the colony, the ordinary dangers of simply being alive don't pause to wait. On Earth, when something goes wrong inside the body, help is close. On Mars, it isn't. There is no hospital, there is no ambulance, no evacuation, no specialist a flight away. There is only the small crew, whatever supplies they carried, and whatever they themselves know how to do. Picture something as routine as a burst appendix, a problem a surgeon on Earth fixes almost casually, that kills reliably without one. On Mars, if no one present can perform that surgery, a healthy person could simply die of it, and even a trained doctor faces a cruel erosion. Skills fade when they go unused, and a physician might go years between the procedures they were trained for, their expertise quietly rusting. The obvious answer, just call Earth for help, runs straight into the wall of distance. A radio signal between the two planets takes anywhere from about 3 minutes to 22 minutes to cross, each way. You cannot talk a surgeon through a crisis when every question you ask takes 20 minutes to arrive, and the answer takes 20 minutes to come back. By the time the reply reaches you, the moment is long gone, and the medicines themselves are not safe either. Drugs lose their strength and expire over the long years of a mission, and Mars cannot manufacture the complex pharmaceuticals to replace them. But the body is only half of it. There is the mind, and the mind in this place may be the most fragile thing of all. Picture the true shape of life on Mars, sealed inside cramped, windowless habitats, the same few faces every single day, mortal danger pressing against the walls every hour, and Earth reduced to a pale dot in a black sky, impossibly far away. We know what that kind of existence does to people, because we've tested it in the closest place on Earth, the research stations of Antarctica, locked in through the long polar winter. Scientists treat those winter overs as a genuine rehearsal for space, and the results are a clear warning. The isolation, the confinement, the endless dark, and the constant low stress take a real toll, bringing on depression, anxiety, sleep that won't come, and friction between people that builds with nowhere to release. We saw the same thing in that sealed glass world in Arizona, where 8 people cut off together, fractured into factions that could barely speak. On Mars, that pressure would be far worse, and the exit far further away. Lock a handful of human beings in a small box, surround them with a world that wants them dead, and cut them off from everyone they have ever loved. And conflict is not a possibility. It is close to a certainty. There is simply nowhere to walk away to. And in the grimmest version of all, someone eventually dies, which raises questions no colony has ever had to answer. What do you do with a body on a world where burial might contaminate the very soil scientists are studying, where every resource is precious, and where the ground itself is frozen and poisonous? Even death on Mars becomes a problem without a gentle solution. But step back for a moment, because we have been describing all of this as if the danger begins the day a person arrives on Mars. It doesn't. Every single thing we've talked about, the bone loss, the wasting muscles, the radiation tearing at cells, the isolation pressing on the mind, none of it waits for the red planet. It begins the moment the engines shut off and the spacecraft starts to drift. In the 6 to 9 months of pure, empty void you must cross just to get there. Months sealed inside a fragile metal shell, falling through the dark between worlds, where the air, the water, and the warmth all depend on machines that must not fail, because if they do, there is no one within tens of millions of miles to help, and somewhere along that crossing, a line is quietly passed, a point after which there is no turning the ship around, no coming home, no changing your mind, not a line drawn in space, a line drawn through a human life, and almost no one who sets out truly understands where it is until they are already on the far side of it. So let's follow that crossing, the empty months between the worlds, because the line we just spoke of is hidden somewhere inside it. The danger of Mars does not wait for Mars. It begins the instant the engines fall silent and the ship begins to drift, with Earth behind it and nothing ahead but the dark. For 6 to 9 months, a handful of human beings will fall through that dark inside a sealed metal shell, kept alive by machines that cannot be allowed to stop, and somewhere along that fall, without any marker to warn them, they will pass a point they can never come back through. Not a border on a map, a threshold in the architecture of the journey itself, and almost no one who crosses it feels the moment it happens. Let's be precise about the crossing. Reaching Mars takes roughly 6 to 9 months of continuous travel through interplanetary space. That is longer than a human pregnancy, long enough that a child conceived the week of departure could very nearly be born before the ship arrives. And for every hour of those months, the people inside are utterly dependent on one thing: a sealed life support system that must manufacture their air, purify their water, and hold their warmth against a void sitting just millimeters away on the other side of the hull. Think of the spacecraft as a single sealed tin can drifting across an ocean with no shore. On Earth, when a system fails, help comes. A hospital, a rescue boat, a phone call answered. Out there, none of that exists. No port, no coast guard, no second ship within tens of millions of kilometers. If the air system falters, if the water recycler clogs, if the heat bleeds away, there is no one to call and nowhere to turn. The crew must fix it themselves with what they carried, or they do not survive it. And as the weeks pass, the thing they are leaving behind begins to shrink. Earth, which fills our entire sky, which is the floor under every life ever lived, dwindles in the window, from a world to a disk, to a point of pale blue light you could hide behind your thumb. That is the moment the isolation becomes real, and while they fall, the unseen damage we have already traced does not pause, it sharpens. Take the radiation. You might assume deep space is no worse than the Martian surface, but the reality is the opposite. On the ground, the bulk of the planet sits beneath you, blocking roughly half the sky, and even the thin air overhead absorbs a little of what comes through. In open space, nothing blocks anything. The radiation arrives from every direction at once. NASA's instruments measured the cruise dose at around 1.8 millisieverts per day, and a single chest X-ray is about 1/10 of a millisievert. So every day in transit, a traveler absorbs the rough equivalent of 18 chest X-rays. Not once, every day, for months. And the body itself is quietly coming apart in the weightlessness, exactly as it does in orbit, bone thinning, muscle wasting, the heart growing lazy. To fight it, the crew must exercise for around 2 hours every single day, strapped to machines, not to grow stronger, but merely to slow the decline. Then there is the smaller, stranger erosion. The food, months of packaged, freeze-dried meals, rehydrated from pouches, the same narrow set of flavors over and over, with nothing fresh, nothing growing, nothing new. That monotony sounds trivial. It is not. Appetite fades, morale sags, and people who are already losing weight begin eating less precisely when they can least afford to. And surrounding all of it, the crew, a few people sealed together in a space smaller than a modest apartment, with no privacy, no door to close, and no way to ever walk away from one another for the better part of a year. Every irritation magnified, every disagreement trapped in the same metal room. There is no exit, not for months. And then, at the end of that long erosion, comes the part that lasts only minutes, and may be the most dangerous of all. Arriving at Mars is not a gentle thing. The engineers who do this for a living have a name for it, and the name tells you everything. They call it the 7 minutes of terror. Here is what those 7 minutes contain. The spacecraft strikes the top of the Martian atmosphere at around 13,000 miles per hour, better than 21,000 kilometers per hour, many times faster than a rifle bullet. It must shed nearly all of that speed and reach a dead stop on the ground in about the time it takes to boil a kettle. First, a heat shield slams into the thin air and takes the brunt of it, heating until it glows at over 2,000 degrees Celsius, more than 3,500 degrees Fahrenheit, as hot as the surface of the sun, hot enough to vaporize most metals. That fire bleeds away much of the speed, but nowhere near enough. So next, a parachute fires open, the largest, strongest supersonic parachute we know how to build, snapping taut with a violence of around 9 times the force of gravity, catching tens of thousands of pounds of force in an instant. And even that is not enough. The thin air cannot finish the job. Still falling at hundreds of miles per hour, the craft must cut the parachute away, drop free, and fire rocket engines downward to lower itself the rest of the way to the surface. Heat shield, parachute, rockets, each one must work. Each must happen in the right order. Each must fire at exactly the right instant. One sensor misreads, one parachute tears, one line of code mistimes, and the whole sequence ends in a crater. We know this is not theoretical, because Mars is littered with the wreckage of missions that got one step wrong. NASA's Mars Polar Lander, Europe's Schiaparelli probe, machines that came so far and died in the final minutes. And here is the detail that turns the 7 minutes from frightening to almost unbearable. Through every second of that descent, the people who built the spacecraft, sitting in mission control back on Earth, cannot help. They cannot steer it. They cannot correct a single mistake, because a radio signal from Mars takes many minutes to cross the distance. During one recent landing, about 11 minutes. Think about what that means. By the time Earth receives the signal that the craft has touched the top of the atmosphere, the entire landing is already over. The spacecraft is already in reality alive on the surface, or already dead. The engineers are watching the past. They sit and listen to faint tones crossing the void, narrating events that have already finished, powerless to change an outcome that has already happened. The craft is completely, irreversibly on its own, but everything I have just described, we have only ever done with robots. And a human mission breaks the problem open in a way nothing before it has. Consider the masses. Every rover we have ever set on Mars weighs roughly 1 ton, about the weight of a small car. A spacecraft carrying human beings, with their habitat and supplies and the vehicle that must one day carry them home, could weigh 40 to 80 tons, the mass of a loaded truck, dozens of times heavier than anything we have ever landed there. And this is where the Martian atmosphere becomes almost cruel. Engineers describe it as a paradox, and the description is exact. The air is just thick enough to set a fast-moving spacecraft on fire and force you to carry a heavy heat shield, yet far too thin to actually slow that spacecraft down the way Earth's dense air would. So you get all of the danger of an atmosphere and almost none of the help. Landing a 1-ton robot in those conditions already sits at the bleeding edge of what we can do. Landing the weight of a truck gently on rockets with people strapped inside, no one has ever come close. It is not a refinement of the robotic landings. It is a leap into territory we have never touched. And suppose they survive all of it, the crossing, the erosion, the 7 minutes, the impossible wait. Even then, the cruelest problem of the entire journey is still waiting. Leaving. You might assume the ship simply refuels for the trip home the way it fueled up to leave Earth. It cannot. The amount of propellant needed to climb back off the Martian surface is staggering, on the order of 1,500 tons for a single large ship, the weight of roughly 10 blue whales. No spacecraft could ever carry that much dead weight all the way to Mars and back. So the plan, the only plan that works, is as audacious as anything in the history of exploration. You arrive with empty tanks and you make your fuel out of Mars itself. Here is the chain that has to happen. Machines must mine water ice out of the frozen Martian ground. That water is split apart by electricity into hydrogen and oxygen. Other machines must pull carbon dioxide out of the thin Martian air. Then, in a reactor running a process, chemists have known for over a century, the Sabatier reaction, that carbon dioxide and hydrogen are combined over a catalyst to produce methane, the fuel, and more water, while the oxygen is captured and frozen to feed the fire. Mine the ice, split the water, capture the air, build the methane, store the oxygen. Every step in that sequence must succeed, using industrial machinery that has never once been run at full scale on the surface of another planet. And now the trap closes, because the crew commits to the journey, crosses the void, burns through the 7 minutes, lands on the surface, long before anyone knows whether that fuel factory will actually work. If it fails, if the ice is harder to reach than the map suggested, if a reactor breaks, if the chain snaps at any single link, there is no propellant. And with no propellant, there is no launch. And with no launch, there is no way home. Not delayed, not difficult, none. This is exactly why every detail of the landing site matters so much. SpaceX's leading candidate is a broad, flat northern plain called Arcadia, chosen above all because the water ice there is thought to lie only centimeters to meters beneath the surface, shallow enough to dig. That single feature feeds everything: the water the crew drinks, the oxygen they breathe, and the hydrogen that becomes the fuel to leave. And the first work on arrival is brutal. Before that fuel chain can even begin, the crew must deploy their power source and life support systems by hand, sealed inside bulky, stiff, exhausting pressure suits in which the simplest task, turning a bolt, dragging a cable, takes hours rather than minutes. All of it against a quiet, merciless countdown. The supplies they brought are finite, and every system must come online and start replenishing air, water and power before those carried reserves run out. And because every person is essential, the crews must be cross-trained across each other's jobs, because in a group that small, losing a single specialist to illness or accident could cripple the entire base. And if, against all of it, the fuel is made and the ship can fly, the journey home is not an escape so much as a repetition, another 6 to 9 months of the same weightless wasting and the same relentless radiation endured all over again in reverse. But here is the constraint that hardens the whole thing into something close to a sentence. You cannot leave Mars whenever you wish. The two planets are racing around the Sun at different speeds, and only at certain moments do they line up so that a journey between them is even possible. Those windows open roughly once every 26 months. Miss your departure, for any reason, mechanical or medical or human, and the next chance to leave is more than 2 years away. Not because anyone decides it, because the orbits of two worlds say so. Once you are there, you are committed, not for days, not for weeks, but for years, possibly for the rest of your life. And so, we arrive, finally, at the line we started with, and at what it truly is. We have been imagining it as a place, the moment the ship can no longer turn around, the moment the parachute opens. But the deepest point of no return was never out there in the dark at all. We traced it already. After years in a third of Earth's gravity, a human body may quietly rewrite itself into something that can no longer survive its own home planet, and a child born under that weak pull may never, from its first breath, be able to leave. That is the real threshold, not a line the ship crosses, a line that is crossed inside the traveller, slowly in their own bones, until the door home has closed not in space, but in the body. Which leaves one question we have been circling from the very beginning and can no longer avoid. If reaching Mars is this punishing, this expensive, this irreversible, then who exactly pays for it? Who is permitted to go, and who decides? Who would own the ground beneath that first habitat, and who grants any of us the right to take an entire untouched world and risk ruining it in order to try? So let's confront those questions directly, because they lead somewhere unexpected. Everything we have traced so far, the radiation, the poison dust, the failing body, the merciless crossing, every one of those is a wall made of physics, and walls made of physics can, in principle, be engineered around, given enough time and enough genius. But suppose we solved all of them tomorrow. Suppose the rockets flew flawlessly, the habitats held, the bodies endured. We would still slam into a second kind of wall, one built not from radiation or gravity, but from money, from law, and from a question almost no one wants to ask out loud, whether we have any right to do this at all. And these walls may turn out to be harder than the physical ones, because they cannot be solved with better engineering. The money comes first, because nothing else moves without it. Building a genuinely self-sustaining settlement on Mars would, by current estimates, cost somewhere between hundreds of billions and several trillion dollars. Even a single launch runs into the hundreds of millions, even with reusable rockets. And a real mission needs not one launch but many, flight after flight, just to assemble and fuel a single crossing. Hold on the word trillion for a moment, because the human mind cannot actually hold it. We hear billion and trillion as neighbours, two words that sound almost the same. They are not. A trillion seconds is not a span of years. It is almost 32,000 years. Count backward a trillion seconds from this moment, and you do not land in ancient Rome or ancient Egypt. You land in the depths of the last ice age, before farming, before cities, before written language, when our ancestors were painting animals on the walls of caves by firelight. That is the scale of money we are discussing, not a purchase, a civilization-sized commitment, sustained for generations. And here is the first cruel twist. You might assume that, like the great colonies of history, a Mars settlement would eventually pay for itself, that it would find something precious in the red ground and ship it home, and the money would start flowing back. Every colonial empire on Earth ran on exactly that logic. Ships sailed out at enormous cost, and they came home heavy with gold, silver, spices, sugar, cotton, cargo worth far more than the voyage. The colony became an investment that returned a profit. Mars can do no such thing, and the reason is brutally simple. The cost of shipping anything back across tens of millions of kilometers, tens of millions of miles, is so staggering that nothing on Mars is worth the trip. Not iron, not rare metals, not even gold. You could find a mountain of solid gold on Mars, and it would still cost more to bring home than it could ever be worth, because the rocket fuel and the years and the engineering would dwarf the value of the cargo. There is no export, there is no profit, there is no cargo that ever sails home, which means the colony can never become self-sufficient the way historic colonies did. It would stay permanently, helplessly dependent on Earth's money, a patient on life support with the power cord running all the way back to another planet. And that creates a vulnerability more chilling than any dust storm. If the government, the company, or the billionaire funding that colony ever loses interest, a market crash, a change of leadership, a war, a simple shift in priorities, the money stops. And if the money stops, the colony is stranded, not rescued late, not helped slowly, abandoned on a world that kills anything not actively kept alive. Sustaining it would demand decades of unbroken political and financial commitment, a kind of steady, multi-generational resolve that human institutions have almost never managed to hold. And the people out there would feel that distance widening in another way too, in every word they tried to exchange with home. We have already seen that a radio signal between the two planets takes anywhere from about 3 minutes to 22 minutes to cross, one way. Sit with what that does to a conversation. You cannot talk to Mars. Not really. You can send a message and wait, and the soonest any reply could possibly return is the round trip of light, which near the worst alignment means waiting the better part of an hour to hear the answer to a single sentence. Every exchange becomes like email, sent across a canyon of time. No interruptions, no laughter shared in the same instant, no comfort offered in real time, just statements, launched into the dark, and long silences waiting to be filled. And then, roughly every 2 years, even that thin thread is cut completely. When Mars passes around the far side of the Sun from Earth, the Sun's outer atmosphere, a vast cloud of hot, electrically charged gas, sits directly in the path of the signal and scrambles it. NASA's own engineers describe it as trying to talk across a giant bonfire. For about 2 weeks, they stop sending commands to their Mars robots entirely, because a single corrupted instruction could doom a spacecraft. For a colony of human beings, that means roughly a fortnight, every 2 years, of near total silence from home. Under all of this, the delay, the silence, the sheer distance, the bond between Earth and Mars would inevitably strain and thin. The colonists' children would be born knowing Earth only as a bright point of light and a voice that always answers late. Slowly, almost invisibly, a distinct Martian identity could begin to form. A separate people with their own rhythms, their own concerns, and eventually, perhaps, their own idea of who they are. And that raises a question no one has answered. Who, exactly, would be in charge of them? Let's be precise about what the law actually says, because it is stranger than most people realize. Back in 1967, more than 100 nations signed a document called the Outer Space Treaty, and it remains to this day the foundation of all space law. Its most famous line is unambiguous. Outer space, including the moon and other worlds, is not subject to national appropriation, meaning no country on Earth is permitted to claim Mars, or any part of it, as its own territory. The treaty even calls space the province of all mankind. Mars, in the eyes of the law, belongs to no nation and to everyone at once. But the same treaty contains a second principle that pulls hard against the first. Each nation remains responsible for whatever its own citizens and companies do in space, and must authorize and continuously supervise their activities. So picture the first permanent town on Mars. No country can own the land it sits on, but the company that built it answers legally to whatever nation it was incorporated in. And the colonists themselves? The treaty says almost nothing about people actually living there. It created no government for Mars, no court, no police, no referee of any kind off the surface of the Earth. The authority over that first settlement is genuinely, dangerously undefined, and the communication delay quietly settles the matter in practice. When every decision must wait 20 minutes or more for Earth to weigh in, the people on Mars cannot wait. They must decide for themselves, in the moment, again and again. They would govern themselves by necessity, a de facto independence, long before any treaty or any nation formally granted it. Newer agreements, like the Artemis Accords that several dozen countries have now signed, are early attempts to patch the holes. But the deepest question remains wide open, and Mars could drift toward becoming its own world, in law as well as in spirit, whether anyone on Earth intends it or not. And then there is the problem that may matter more than all the others, the one we carry in our own bodies and cannot put down. Wherever a human being goes, an invisible multitude goes too. Your body right now carries trillions of bacteria on your skin, in your gut, in every breath, and no amount of scrubbing, no sterilization we possess, can ever fully remove them. So the instant a human sets foot on Mars, Earth life arrives with them, permanently, irreversibly. We would contaminate that world with our own microbes the moment we touched it. For decades, that was a theoretical worry. As of September 2025, it is not, because NASA announced something that changes the weight of every word in this conversation. The Perseverance rover, examining a rock nicknamed Chayava Falls in an ancient dried-up riverbed, found the strongest potential sign of ancient life ever discovered on Mars, a pattern of minerals and organic carbon that, here on Earth, is most often created by living microbes. The scientists were careful, and they were right to be. They did not say they had found life. They called it a potential biosignature, a feature that might come from biology, but that needs more study to be sure. Still, standing at that press conference, NASA's own science chief said they believed these marks were potentially made by some form of ancient life, a leftover sign, the closest we have ever come. Now hold those two facts side by side. We may be about to send human beings, crawling with Earth bacteria, to the one world where we have just found the best evidence that life might once have existed. Think about what that collision means. The very act of going to search for Martian life could be the act that destroys it. Our microbes could overrun whatever fragile traces remain, or they could so thoroughly contaminate the rocks that we could never again tell what was native to Mars and what we tracked in on our boots. We could erase the answer to the oldest question we have ever asked by reaching for it, the thing we crossed the void to find, smothered by the hands reaching to touch it. Let's come back to the dream that sells all of this. The vision of a future Mars turned green and warm and breathable, where people walk beneath an open sky without a suit. It is a beautiful image, and it runs directly into the evidence. In 2018, two scientists, Bruce Jakosky of the University of Colorado and Christopher Edwards of Northern Arizona University, gathered roughly 20 years of spacecraft data and asked plainly whether we could warm Mars by releasing the carbon dioxide locked in its soil and ice. Their answer was stark. There is simply not enough accessible carbon dioxide left on Mars to do it. Most of the planet's ancient, thicker atmosphere was stripped away into space billions of years ago, and that gas is gone forever. Even if you released everything you could practically reach, it would barely warm the planet at all, and waiting for Mars to rebuild its own atmosphere offers no escape. At the rate the planet currently releases gas from its interior, the researchers calculated it would take about 10 million years just to double the thin air that exists today. And even doubling would not be remotely enough. 10 million years, long before the first true humans existed, before our ancestors had even split from the other great apes. By the best science we have, terraforming Mars is not a project for this century, or the next, or any century we can foresee. With anything close to today's technology, it is effectively impossible, a fantasy that may one day belong to some far future capability we cannot yet even imagine. But that does not belong to us. The green Mars is not coming. Not for us. Not for our great-grandchildren. The data simply will not allow it, which leaves the hardest question of all. Not can we, but should we, and who decides? The treaty says Mars is the heritage of all humankind. But look at what is actually taking shape. The first Mars is being designed by a vanishingly small number of people. A few governments, a few enormous companies, a few of the wealthiest individuals who have ever lived, making choices that could shape the entire future of our species and risk permanently altering an untouched world, while the other 8 billion of us have no vote and no voice. To some, this is the noblest insurance policy imaginable, a second home for humanity, so that life does not keep all its eggs on one fragile planet. To others, it looks like something far older and darker wearing a new suit, a colonialism reaching off-world, taking in practice what the law insists no one is allowed to own, and deciding the fate of a whole planet on behalf of a species that was never asked. And so we have walked the entire distance. We began with a seductive dream and a lethal doorstep. We crossed the invisible fire of radiation, the unbreathable air and the poison dust, the fragile machines that must never fail, the body that quietly betrays anyone who stays too long, the merciless crossing and its hidden point of no return. And now, finally, the money that runs out, the law that has no answer, the microbes we cannot leave behind, and the green future the evidence refuses to grant us. One by one, we have counted every reason that the reality is harder, lonelier, more dangerous, and more irreversible than the dream ever admits. Only one question remains. It has been sitting underneath all the others from the very beginning, beneath that first pale red light in the night sky, beneath every fact we have uncovered since. Now that we truly know what it would cost, in money, in bodies, in risk, in the possible ruin of two worlds at once, we have to ask it directly and answer it honestly. Should we go at all? So here we are, at the end of the long road, holding the only question that was ever really worth asking. Should we go? Not whether we can dream it, or film it, or sell it, but whether we should actually do it, spend the fortunes, risk the lives, reach for that cold red world with human hands. To answer honestly, we have to set down two things at once: the breathless hype that promises a city by next decade, and the lazy cynicism that says it could never be done at all. Both are easy. Neither is true. And the most surprising thing we will find, now that we know what Mars really is, has almost nothing to do with Mars. It has to do with the world beneath you right now. Consider the sentence that launches 1,000 colonies. Whenever someone raises a problem with living on Mars, the most common answer is 3 confident words. It's just engineering. And sometimes that answer is right. Humans are the finest engineers this planet has ever produced. We have crossed oceans, split the atom, and landed machines on that red surface from 100 million miles away. Many Martian problems, better shielding, tougher habitats, smarter recycling, are genuinely just engineering, and given enough time and money, we will almost certainly solve them. But here is the trap hidden inside those 3 words. Some of the barriers on Mars are not engineering problems at all. They are not bugs in a system waiting to be patched. They are the permanent nature of the place. You cannot engineer your way out of 1/3 of Earth's gravity. That number is fixed by the size of the planet itself, and it will press on every bone and every heart for as long as anyone stands there. You cannot restart a world's dead iron heart, the churning core that once gave Mars a magnetic shield and fell still billions of years ago. And you cannot put back an atmosphere that was stripped away into space across eons and is, quite simply, gone. No clever device fixes these. They are not waiting for a better invention. They are what Mars is. So let's weigh the real reasons people give for going anyway, one honest argument at a time. The most powerful argument, the one that stirs something deep in us, is survival. Mars as humanity's backup, a second basket for our eggs, so that one asteroid, one war, one catastrophe cannot end us. As a feeling, it is almost irresistible. But let's hold it up to the light. Picture the very worst thing that could happen to Earth: a massive asteroid strike, an all-out nuclear war, the most extreme runaway warming imaginable. Now ask a simple question. After that disaster, which planet is more survivable? The answer is not close. Even a devastated Earth, scorched, irradiated, frozen, whatever the nightmare, would still hold breathable air in its skies, liquid water on its surface, a magnetic field overhead, and temperatures a human body could endure. Mars offers none of those things on its calmest, best day. The most ruined version of our planet would remain kinder to human life than Mars will ever be. And the colony meant to be our insurance carries a deeper flaw still. It would depend on a constant stream of supplies and spare parts from Earth simply to stay alive. So if Earth's industry ever truly collapsed, the very scenario the backup is meant to outlive, the colony would not save us. It would die a few years later, a lifeboat that sank because it was still roped to the ship. Even Robert Zubrin, the founder of the Mars Society, and perhaps the most devoted advocate for settling Mars alive today, rejects this framing entirely. He argues we should go not in despair, fleeing a doomed planet, but in hope to plant something new, which is a beautiful reason, but it is a very different reason from survival. And then there is the gentlest argument of all. Exploration is human nature. It is who we are, the restless drive that carried us out of Africa and across every ocean. That is simply true, and it is one of the best things about us. But notice the quiet sleight of hand inside it. Exploring is not the same as permanently colonizing. We sent people to the deepest trench in the ocean and to the frozen heart of Antarctica, and we learned to revere those places without building cities of millions in them. To visit Mars, to study it, to stand on it, that is exploration. To move there forever is something else entirely, and the first does not automatically justify the second. Let's be honest too about how close this future actually is, because the dream has a long history of slipping through our fingers. For years, the public dates for humans on Mars kept arriving and quietly passing. A crewed landing promised for the mid-2020s, then pushed again. And then came the most telling moment of all. In February of 2026, SpaceX, the company that has driven this entire dream, abruptly changed course announcing it would focus first on building a base on the Moon and delay its Mars ambitions by another 5 to 7 years. The planned launch of uncrewed ships to Mars in that very window was shelved. Think about what 5 to 7 more years means. More than 2 entire Martian launch windows opening and closing with no one aboard. A child born the week of that announcement, walking into school before the first ship even tries again. And the obstacles underneath are not small. One hard prerequisite for any Mars journey, transferring fuel from one spacecraft to another in orbit, has still never been successfully demonstrated. And perhaps the most sobering voice belongs once more to Robert Zubrin, the man who wrote the book on settling Mars, who wants this more than almost anyone alive. Even he calls the near-term timelines unrealistic, a landing in the next few years effectively impossible. The most committed believer on Earth is telling us the schedule is a fantasy. By any sober reading, a real human outpost on Mars is plausibly decades away, and true self-sufficiency, a colony that could survive on its own, perhaps a century or more beyond that. The vision of a thriving, self-sustaining city by 2050 looks less like a plan and more like a wish. But here is the collision that brings the whole question into focus, and it unfolded in the span of just a few months. Consider the single best reason to go to Mars at all, to answer the oldest question we have ever asked. Did life ever exist beyond the Earth? In September of 2025, we came closer to that answer than ever before in human history, and we did it without sending a single person. A robot, the Perseverance rover, examining a rock called Chayava Falls, found the strongest potential sign of ancient life ever discovered on Mars. A machine reached the very edge of the greatest discovery we could ever make, but that potential sign cannot be confirmed on Mars. To know for certain, the sample has to come home to the great laboratories on Earth. And here is what happened next. Within months, by early 2026, the government funding the mission to retrieve it effectively cancelled that mission, judged too expensive. The cost of bringing those samples home had climbed to around $11 billion, and even trimmed closer to $7 billion. It was deemed more than we were willing to pay. So consider where that leaves us. The most precious rock humanity has ever collected, possibly holding the answer to whether we are alone in the universe, now sits sealed in a metal tube on the surface of Mars, with no funded way to bring it back. We found, perhaps, the most important evidence in the history of science, and we could not find the money to go and get it. Sit with that for a moment, because it quietly reveals the truth the dream keeps hidden. The robots are already at the frontier. They are already doing the science, finding the rocks, reading the chemistry, standing exactly where the discovery is, at a tiny fraction of the cost and none of the risk of sending a living person. The $11 billion we would not spend to retrieve that one sample is a rounding error beside the trillions a human colony would demand. The frontier of discovery, it turns out, does not require human bodies on Mars at all. It requires only the will to pay for the machines already standing there. So let's weigh all of it, plainly, the way you would weigh anything that truly mattered. The technology spun off from space programs is real and valuable, but you reach those technologies faster by investing in them directly than by routing through a Mars colony. The inspiration is real too, but inspiration is deeply personal, and 1,000 different things inspire 1,000 different people. The survival argument is the most emotionally powerful of all, and the most logically fragile. And beneath every one of them sits a hard truth. Every dollar sent to Mars is a dollar not spent on. The problem's already crying out for it here at home: a changing climate, diseases still without cures, poverty that ends lives every single day, and, with a bitter irony, the defense of Earth against the very asteroids the backup argument fears most, a danger we could actually reduce right now for a fraction of the cost. The honest answer then is not never. It is not like this. Keep exploring Mars with our brilliant robots, who are already succeeding beyond anything we dared hope. Patiently mature the technology until a human journey is something other than a gamble with lives, and send people only when the risks have genuinely been minimized and the hard ethical questions, the contamination of a possibly living world, the children who could never consent, the colonists with no clear law to protect them, have been faced with honesty rather than waved away. We should reach for Mars not for one person's lifetime, not for any nation's pride, not for any company's profit, but carefully, together, when we are truly ready. You are allowed to love this dream and still tell the truth about it. In fact, telling the truth about it may be the only thing that could ever make it real. And now, at the very end, the question quietly turns into something else, because the deepest terror of Mars was never that it is difficult. Difficulty we could respect. The real horror, the thing that settles over you once you have seen the whole picture, is how completely, how utterly that world rejects us. Every danger we have traced is not an obstacle to be overcome. It is simply what Mars is, and what it will always be. Radiation pouring down through a sky with no shield, air that cannot be breathed, cold that kills in hours, dust laced with poison, a pull too weak to hold a body together. None of them flaws, none of them fixable, all of them just the truth of the place. And standing in the cold light of that rejection, something turns all the way around. We set out searching for another home, and what we found in the searching was how impossibly, improbably gentle this one already is. Go all the way back to the beginning of this journey, before you knew any of what you now know. You took a breath, and you did not notice it. You have not noticed almost any of the roughly 20,000 breaths you will take today, each one delivered free, in exactly the mixture your body needs, at exactly the pressure that keeps your blood from boiling inside your veins, warmed to exactly the temperature you can survive. You never asked for a single one of them. You never felt them arrive. But now you know what that breath would cost anywhere else. The machines that would have to manufacture it. The 2 minutes between you and death if those machines failed. The unimaginable effort to build on a dead world. The one thing this living one hands you for nothing, every few seconds, for your entire life. That unnoticed breath was never ordinary. It is the rarest luxury in the known universe, and Earth gives it to you freely, without being asked, and asks for nothing in return. The same is true of the water you drank today without ever tasting your own good fortune. The same is true of the sunrise this morning that you almost certainly did not stop to watch. Years ago, the astronomer Carl Sagan looked at a photograph of Earth taken from beyond the orbit of Neptune. Our entire world shrunk to a single pale blue point of light, smaller than a speck of dust against the dark, and he saw, gathered on that one tiny pixel, everyone who had ever lived, every ruler and every child, every saint and every fool, everyone who ever loved another person, the whole of human history, all of it on a single speck of light, adrift in an enormous and silent dark. After everything we now understand about the alternative, his reflection lands harder than even he could have known. For all its flaws, all our conflict, all our trouble, all the ways we fail one another, that pale blue dot remains, by an overwhelming margin, the kindest place in the entire known universe, the only door that has ever opened for us, the only one, perhaps, that ever will. So maybe that is the real gift of the dream of Mars. Not a second home, a mirror. We reached across the dark for another world, and what it handed back to us was the truth about this one. The question, in the end, was never really whether we could someday learn to live on Mars. It was whether we would understand, before we squander it, before it is ever too late, how astonishingly rare, how fragile and how precious the home we already have truly is. You are standing on it right now. Take a breath, and this time, notice it. Somewhere above you tonight, if you stepped outside, you could find it. Mars, a faint red point in the dark, a whole world, a possible future. And for these past hours, we have reached toward it together. But turn your eyes back down now, back to the room you're sitting in. Maybe someone is asleep just down the hall. Maybe someone who should still be here isn't. Every voice that ever said your name, every face you have loved, every hand that ever held yours, all of them belong to this one small world, not to that distant red light, to this. Mars may one day offer us a future. It can never give us a past. It cannot hold the people who made you or the years you have already lived. Home was never a place waiting to be built out there in the cold. It has been here the whole time, beneath your feet and in the people breathing in the rooms around you. Thank you for walking this long road with me tonight. If it meant something to you, a like and a subscribe are how you let me know. Stay close to them tonight. You are already home. Sleep well tonight. Good night.